Okay, so let's talk about multi-core issues in caching. I want to spend some time over here because multi-core imposes a lot of other interesting issues in caches. And as we discussed, all of our systems are multi-core, right? So in this system, for example, L1 caches were private. I believe L2 caches were also private. L3 cache was shared across processors. So even that's a design decision that you need to make, right? Which caches are shared by which cores? And then do you design higher level caches that are shared, etc. So you're used to these pictures right now. I will mention this cache over here because it's very interesting. This is a shared cache that's on a different chip. So basically, they've decided to add these other, let's say, other chips that are bonded on top of a processor chip. And the whole purpose of the other chip is to cache. And there are a lot of actually really interesting technology issues, like how do you align the interconnects in this chip with this chip over here so that they can actually communicate with each other nicely. So there are a lot of fabrication and reliability issues over here that we take for granted right now. But these are two different chips bonded together on top of each other. And the whole purpose of the second chip is just caching, basically. Caching for all of those cores that are in the other chip. And there are many cores over there. Okay. So basically, cache efficiency becomes a lot more important in a multi-core or multi-threaded system. If you have a single thread accessing the cache, that's nice, you can manage it. But then if you have 10 different threads or 20 different threads or 100 different threads accessing the same cache, now you got to be a lot more efficient. The same is true for memory bandwidth. Actually, memory bandwidth is even more important potentially. So that's why there have been a lot of research in multi-core systems or caching for multi-core systems. Basically, memory bandwidth is at premium. You don't want to go to main memory. You want to basically ideally hit in caches. Unfortunately, it doesn't happen. And also, a cache space is a limited resource across cores and threads. So both space and bandwidth are problems. Then the question becomes, how do we design caches in a multi-core system? There are actually many interesting design decisions over here. Should they be shared or private across cores or threads? We're going to look at this one. How do you maximize the performance of the entire system as opposed to just a single thread that we've been talking about so far? How do you provide quality of service to different threads? How do you provide predictable performance? If some thread, for example, needs really hard deadlines, because it could be a GPU, for example, it needs to display a frame on a video frame, for example, on the screen. And if you actually skip some things, that's not going to be great for the quality of service provided to the user. It could be a safety critical thing also. Basically, there are a lot of interesting issues over here. Should the cache management algorithms be aware of the different threads accessing them? Right. We have not talked about this so far, but maybe yes. And how should space be allocated to threads in a shared cache, assuming that you actually want to do the space allocation across different threads? And then there are other issues, like if the bandwidth is at premium and if the space is at premium, should you actually start compressing the data that's in your caches? It's actually, I think, an important area. And people have been looking at compressing data inside the caches, compressing data inside the memory so that they can actually store more data, reducing the redundancy and waste in the data. And also, how do you do better reuse prediction and management in caches? We've been talking about reuse prediction and management, but you need to do better in all of these. And there may be other questions also. But let's take a look at one dimension of this, which is basically, should the cache be private or should the cache be shared across cores? Or a subset of cores, right? You could generalize this. So a private cache, a cache belongs to one core, which means that a shared block can be in multiple caches. Right? Whereas a shared cache is shared by multiple cores. Basically, the L2 cache over here is shared by multiple cores, as you can see. And if there is a block that's shared across those different cores, it doesn't need to be replicated across different caches, essentially, if the cache is shared. A block is in only one place, essentially. So you can see there's one immediate advantage of a shared cache. It reduces the replication across different private caches, right? So I'm not even talking about L1 caches. As we discussed yesterday, L1 caches are very tightly coupled with the core. So the design decisions are usually, oh, it's obviously private, right? Because it's part of the core, right? Whereas L2 cache is outer cache. So maybe it's not private, maybe it's shared. Today, some L2 caches are private, some L2 caches are shared, but L3 caches are almost always shared today. Well, I should probably say always shared. Okay, so basically, this is the concept of resource sharing. So if you look at the private caches over here, you're dedicating the cache to the core, and each core has a cache associated with it, L2 cache. But if you look at this other shared cache, you're sharing the resource. instead of dedicating a hardware resource to a hardware context, more generally, we allow multiple hardware contexts to use it. So it could be core, it could be thread, because we can have multi-threading within a core also, right? So it's good to think about this. Essentially, that's the concept of resource sharing. And the resource sharing can be many things. It could be functional units that are shared. It could be the pipeline that are shared. If you remember the fine-grained multi-threading, we shared the pipeline, we shared the functional units, we shared the entire pipeline essentially across different threads. It could be the caches as we've discussed, but also it could be the buses, memory, interconnects, and storage. A lot of those actually are shared across threads because they're too expensive to replicate. Buses are expensive, memory is expensive, interconnects and storage are expensive to replicate. So you do share them across different threads. Caches are, some of the caches may not be too expensive to replicate. So what is the benefit of resource sharing? Why do we share resources? Because it improves utilization and efficiency. That leads to higher throughput, higher performance. Why? Because when a resource is left idle by one thread, another thread can use it, right? There's no need to, and also there's no need to replicate shared data. These are two different things actually. I've given you the example of instruction versus data caches yesterday, right? If you actually partition them, it's the same example basically. You have two different cores, core 1 and core 2. If you actually have private caches of 64 kilobytes each, one core may be using 1 kilobyte of its own private cache, another core may be needing 127 kilobytes. But if you dedicated 64 kilobytes and partitioned it across different cores, the core that needs 127 kilobytes would be unhappy. The core that has that needs only 1 kilobyte would be happy, but it would be underutilizing its cache. So you'd basically waste space because of this. If you had a shared 128 kilobyte cache for both of them, both of the cores would be happy and you would not be wasting space, right? And you would not be increasing the execution time with the same amount of resources. So basically, that's the advantage of resource sharing. It improves the utilization and efficiency, and hopefully that improves performance in the end. And also, there's no need to replicate the shared data, which we also discussed, which we're going to discuss when we talk about cache coherence as well. But there are other benefits, which one benefit is it reduces communication latency. Data shared between multiple threads can be kept in the same cache in multi-threaded processors, for example. If you have a shared cache, for example, you don't need to go to some other cache to get the data that's shared with someone else. As we will see in cache coherence, you may need to do that actually. It's in a shared location. Everybody accesses that from that shared location. It could be in the L2 cache, but you could also think about this in the L1 cache, right? In the L1 cache, you have multiple threads, and multiple threads are sharing a cache block, and they can access it quickly from the L1 cache. Okay. And also, this is compatible with the shared memory programming model, because in shared memory programming model, different threads actually communicate with each other using load and store instructions. One thread stores to a location, another thread reads from that location. Have you guys seen the shared memory programming model in any courses? Parallel programming? Not yet? Somewhat? Okay. Who has not seen it? Okay, some people have not seen it. Who has seen it? Okay, we see almost 50-50 over here. who may have seen it but doesn't remember if they have seen it. Okay, that's good. It's good. It's good that you're honest. But in shared memory programming model, memory is shared across different threads logically and also physically normally. But whenever a programmer writes a program, a thread can do a store to a memory location. Another thread can see that store and load from that memory location. That's how you can synchronize between the threads, for example. We're going to look at that in cache coherence also. And this is sharing of a cache is very compatible with that model, right? That model says there is a single memory, and anybody can see that memory, read from that memory, write from that memory. It doesn't talk about replication of memory, right? Caches, private caches are essentially replicating pieces of that memory locally next to the processor, right? So it's, in a sense, it's not, from a principled perspective, it's not compatible with that model. Of course, it's compatible in the sense that this is all under the hood, right? You're still obeying the shared memory programming model from the software perspective. Okay, so these are actually the advantages. But unfortunately, resource sharing has disadvantages as well. One of the major ones is it actually results in contention for shared resources. When the resource is not idle, another thread cannot use it, basically, because somebody occupied that resource. Right? That's true for any kind of resource. It could be cache space, it could be bus bandwidth, it could be some memory space, it could be some storage space. Basically, if the space is occupied by one thread, another thread needs to reoccupy it if it actually wants to use it. And this leads to reduction of performance. It could reduce each thread's performance. It could reduce some threads' performance. If you're lucky, maybe it doesn't reduce anyone's performance because the block you're evicting is not going to be reused by the thread that occupied it earlier, right? For example, right? But Usually, it leads to some performance reduction for some thread or all threads. Basically, thread performance can be worse than when it's run alone, and that's actually true in many cases. The other issue, which is different from this performance is performance degradation. But the resource sharing, if it's not controlled, leads to performance isolation or eliminates performance isolation. Basically, you get different amounts of cache space, for example, allocated to you based on who's running together with you in the shared cache, right? You may be running with different applications at different times. So you optimize this beautiful application that you wrote it very nicely. You fit it in the cache, in the L2 cache you thought you would have. And when you run it with application A, you get that amount of cache, so your performance is great. When you run together with application B, that application B is very aggressive. It kicks out all of the cache blocks that you need to have in the cache because you optimize your program, and your program's performance is terrible. So this eliminates performance isolation. The programmer was programming or optimizing for hardware, assuming that it would get some amount of cache, right? But you didn't get that amount of cache because the resource was shared across different threads. And the programmer has no control over that clearly. The system has control over which threads are scheduled with each other. And as a result, all of your optimizations are essentially useless, let me put it that way. So that's the importance of performance isolation. You may optimize your program and you may not, if you get performance isolation in the resources, meaning that you actually get the assumed resources in hardware, then your performance is predictable across different runs. Okay, so this is the downside of not having performance isolation because you get very inconsistent results in terms of performance. And also this degrades quality of service, which is related to performance isolation. So if you don't control this sort of sharing, you can have unfairness or starvation. Essentially, some thread may be hogging the resources, and another thread can be delayed indefinitely, if you will. We're going to see examples of this maybe in a later lecture, but I'm going to actually show you an example with the caches soon. So we could keep adding some more over here, but basically you need to efficiently and fairly utilize shared resources. If you're actually doing resource sharing, if you say I'm going to share the cache, you need to have mechanisms to do this efficiently and fairly, such that you get quality of service and you get performance isolation if it's needed for the programs. Again, we're not going to go into how to do this. I'm just foreshadowing some of the problems that exist in modern systems. In fact, some processors have quality of service mechanisms incorporated into them right now. Intel, for example, has a way of partitioning the cache across different applications, and some amount of control on partitioning the memory bandwidth as well. This didn't exist actually 15 years ago, etc., or even more recently, maybe 10 years ago. Okay, now let's analyze this private versus shared caches from this resource sharing perspective. As I said, private cache belongs to one core, shared cache is shared by multiple cores. So what is the advantage of shared cache? You get high effective capacity. Anyone can utilize this big cache, right? That's good. You don't basically, you don't have this fragmentation inside the cache. Because you dynamically partition the available cache space, there's no fragmentation due to static partitioning. And if one core doesn't utilize some space, another core can. So this is nice, clearly. And it's also easier to maintain coherence. We're going to talk about that. It's because a cache block is in a single location, right? It's not replicated across caches, which means that if one processor updates it, it's fine. Everybody sees that update because it's shared, right? So that's good. And we're going to see coherence a little bit more. So the disadvantages, actually, we have not talked about this, but if a resource is shared, you cannot customize it to a single processor, for example. Whereas if you have a private cache, you can customize it, you can couple it tightly with the core, and it can actually have very high throughput. Whereas it's shared, you need to have some sort of network to communicate between the cores to the cache, right? Assuming the cache has a lot of banks, for example, to service. So basically, you get slower access in the end. And as we discussed, cores incur misses by evicting each other's blocks, essentially. These are misses due to intercore interference, if you will. And some cores can destroy the hit rate of other cores, basically, depending on the access patterns again. Right? One core may have very nice locality in the cache, but it may be using, I don't know, 10% of the cache, shared cache. A very small amount of cache. It may need a very small amount of cache. The other core may be streaming through memory, and actually it needs 10 times the size of the cache. When they actually share the cache, the second core actually kicks out all of the blocks that the other core would otherwise have if it were actually running alone in the system. So basically, that's what happens. I'm going to demonstrate this pictorially as well. And essentially, guaranteeing a minimum level of service or fairness to each core becomes harder because of this sharing. How much space do you provide? How much bandwidth do you provide? You need to answer these questions, actually, when you're designing the resource. Okay, let me give you an example. Basically, if you look at this example, we have 2 cores, very simple. Thread 1 is running on this core. And when it's running, it demands almost all the cache, as you can see, L2 cache. Thread 2 is running on this other core, and it demands some of the cache, let's say, when it's running alone. And when they run together, thread 1 occupies most of the cache because it may have a very intensive access pattern, right? And as a result, thread 2 gets much less than what it really needs to get high performance. Maybe it gets nothing almost, right? Because thread 1 actually can be very intensive in terms of memory accesses. So it could be generating 10 requests at the same amount of time. T2 is generating 1 request, for example, right? It could be 100 actually. It could be very, very widely different. As a result, thread 2's performance may be significantly reduced due to this unfair cache share. And this is a real problem in existing systems. That's why you need to design the resources to be shared, assuming you want the benefits of sharing. But also, you should not allow this to happen in existing systems. Okay, I could go on and on, but unfortunately, we're not going to go into how to do that. Basically, resource sharing and partitioning are at odds with each other. Sharing improves resource utilization, for example, better utilization of space. Partitioning provides performance isolation or predictable performance because it dedicates space to a single thread or a single core. The key question is, can we get the benefits of both? And the idea is basically have sharing in the resources, but design mechanisms in those shared resources such that they're efficiently utilized, controllable, and partitionable. So you need to have mechanisms to have controlled sharing, essentially. And the hope is that this way you have no wasted resource, which is a problem with dedicated space, partitioning, and you have quality of service mechanisms that you added to avoid the problems that you have with sharing. Okay? Unfortunately, you're not going to get the perfect upsides of both, but you're going to get most of the benefits of both if you do this. And again, we don't have time to go over this. These are more advanced topics, but you can look at future slides or take courses, etc. Actually, there's a lot more over here. I don't have time to cover, but these issues exist whenever you have shared resources. And in modern systems, resources inside the core are shared across threads. So there's resource sharing inside the core. There's resource sharing outside the core. And outside the core, after some point, everything is shared across many threads. Imagine you have thousands of, 10,000s of threads, and they're really sharing a memory. And memory bandwidth is limited. This is what we see in today's multi-core systems and GPUs, for example, or machine learning accelerators. So basically, there are a lot of issues that you see today. Okay, so let me give you another dimension over here, which is cache coherence. How many people have learned about cache coherence? Let me ask you the same questions. How many people have not learned about cache coherence? How many people may have learned about cache coherence, but they don't remember? That's okay. Okay, so let's learn about cache coherence because this is important. So basically, we have the shared memory programming model, as we've discussed. Threads and parallel programs communicate through shared memory. Thread 0 writes to an address, and thread 1 reads from that address. This implies some communication between two. This is how you can communicate between threads. And also processes, right? Processes are actually larger entities which may contain many threads. So this is one example. This thread is running on processor 0. It's writing to memory location 8. This thread is running on processor 1. It's printing memory location 8. So there needs to be some communication, as you can see over here. Now, if this is the model, each read that happens should receive the value last written by any processor, right? Otherwise, you'll have inconsistency in the program. And there needs to be some proper synchronization between the threads, which we're not going to get into. That's a higher level concern. Basically, the programmer needs to synchronize these threads such that there should be an agreement among the threads as to what is last written mean, right? You use locks, barriers, etc., to do this synchronization, which we're not going to cover here. So we're going to cover the issue with caching. Basically, if you have memory location A that's cached in either processor, we have a problem, basically, because the processors may not see the updates of other processors unless you do something special, which is called cache coherence, essentially. So the basic question is, if multiple processors cache the same block, same cache block, how do they ensure that they all see a consistent state for that particular cache block, right? So we have 2 processors over here, processor 1, processor 2. They have private caches, cache 1 and cache 2. And there's some network through which they communicate to main memory. And we're going to look at this particular cache block X, whose value is initially 1000, right? So let's take a look at what these processors do. Let's say processor 2 loads X into some register, or part of X into some register. Let's say the value it loads is 1000. That's nice. The X gets cached. What is that sound over here? Am I doing this or? No, it's just the tick tick sound. No, maybe this is too close. Okay, so basically this location X gets cached in this cache. And let's assume that processor 1 does the same thing. It loads X into its own R2, and this location gets cached over here. And then processor 1 does something else. It basically does updates location X. And this update gets reflected in the cache. It's a write-back cache, let's say. Now you have inconsistency, right? Main memory is not updated, and this cache is not updated. Then the question is, what should this processor load? When it loads X, should it load 1000? Actually, the easiest answer is should not load 1000. But this also depends on something else, which I don't want to get into, which is the memory consistency model. But the intuitive answer is really this should not load 1000, right? Because the value got updated before you actually should read 1000, right? You should really get the most up-to-date value, assuming the program is synchronized in a particular way. Makes sense, right? That's the intuitive answer. There is a much more complicated answer that requires you to really understand memory consistency, but that's something you should really look at in advanced courses. Okay, so a basic idea is how do you actually ensure that this processor doesn't load the wrong value? That's the basics, basically. Well, the first idea is basically whenever this processor does a write, it broadcasts that it's going to do a write to that block, and everybody who has the block in their cache invalidates the block. Right. This is a very basic cache coherence protocol. It's a broadcast-based cache coherence protocol. You should not write to this block until you're sure that everybody has invalidated the block. Right? That's one answer. The other answer is while you're writing to the block, you also write to all of the other cache's blocks. Basically, you broadcast the fact that you're writing and also the data that you're writing. Here, update your cache block because I'm writing to it. That's the idea. So that's the idea of a broadcast-based protocol. A processor or cache broadcasts its write or update to a cache block to all other processors. And another processor or cache that has the block either invalidates or updates its local copy of the block. Right. So then the question becomes, do you invalidate, do you update? We're not going to get into that. That's a more advanced question. But if you invalidate, that's enough, basically. And if you ensure that there are no race conditions, meaning that someone else doesn't read the old value of the block before that write actually happens, then this should be okay. Okay, that's the idea, basically. And this works nicely if the processors are connected through a medium or caches are connected through a medium where broadcasts are immediately visible to all of the other caches, which is essentially a wire, right? Which is a bus in this case, okay? That limits the scalability of these protocols in general. So let me give you a very simple cache coherence scheme. I'm not going to go into the detail, but because it implements whatever I said, basically. Whenever a processor writes to a cache block, it sends a broadcast message saying that I'm writing to the cache block, and everybody else invalidates the cache block if they have it in the cache. So all caches somehow observe each other's write and read operations. If a processor writes to a block, all others invalidate the block. So a simple protocol with some assumptions. You can study this on your own. Local processor can do read or write to the cache block. And based on those actions, bus read and bus write are broadcast on the bus for the block. And this is what the protocol looks like. It has two states. Because it's a write-through cache, it doesn't have a dirty bit. That's the simplest protocol. So basically, you have a valid state or invalid state. If a processor writes to that cache block, it has to be valid, hopefully. Then it sends a bus write signal. This is the input, this is the output. And whenever a processor sees a bus write in its valid state to a given block, it makes the block invalid. Right? This is a very simple state machine that you're used to right now. Right? And that's the idea, basically. With these assumptions, this is a working coherence protocol. And you didn't really increase the number of bits that you have in the valid bits, let's say. Normally, in coherence protocols, you actually need to increase the number of bits, if you will, because you may need to track modified, for example, and exclusive, etc. But we don't have time to discuss all of that. Makes sense, right? Okay, let me give you another coherence protocol. We'll not go into a lot of detail, but I have to cover this because modern protocols are a combination of both. They're both broadcast-based, but they're also directory-based. So the idea in the directory is have a middleman. Have a middleman arbitrate updates to a cache block or request to a cache block. And that middleman is called the directory. That middleman is logically centralized. But of course, if you want to scale a system, you don't want centralized components. So that middleman is usually physically distributed across different memories, but we're not going to talk about that. Essentially, imagine a central directory that keeps track of which caches contain every possible cache block. Every cache, before doing something to the cache block, consults this directory and asks for permission. Basically, I want to write to this cache block X. Can I do it? It basically goes to the directory. In this case, it's next to the main memory, but directory can also be cached actually next to the caches. So that's very fascinating. You can cache the directory that provides cache coherence. So caching is so powerful because this is actually huge. This thing is huge. And if you take the computer architecture course, you'll calculate the size of it and you'll see that it's huge. But basically, whenever you're writing to X, processor 1 wants to write to X, processor 1 says, I want to write to X directory, please give me permission. And the directory says, okay, let me see who else has X, because it has a bit vector that keeps track of which other caches in the system actually have X, which means that you need to have a bit vector or some data structure for every single cache block in the system to keep track of who has that cache block in their caches, right? Assuming that you have that data structure, directory says, oh, I think I know that cache 2 actually has cache block. I'm going to send a message to cache 2 and ask cache 2 to invalidate that cache block. And after it receives responses from all of the caches that have the cache block saying that they've invalidated the cache block, directory tells cache 1 or processor 1, go ahead, you can write it. You have the only permission or the only copy. Makes sense, right? So this is basically a middleman. Clearly, this middleman is costly because you're going through a middleman, this is an indirection. And as a result, the latency of this coherence scheme is much longer than the latency of what we have discussed over here, right? Here, one processor broadcasts, everybody sees, you don't need to go through any middleman. So that's much lower latency. But this is not scalable because if you want to actually have 200,000 processors connect to a single bus, good luck with that. Even more than 16 is not easy, unfortunately, today. But we have today multiprocessors that are on the orders of tens of thousands, right, that are connected to each other. And that's why, well, this is the reason why we have things connected, assuming you have cache coherence, of course, right? Okay, so I will not go into this detail, but whatever I described applies. An example mechanism looks like this. For each cache block in memory, you store p+1 bits in the directory, and that's costly. Now imagine doing a calculation of this. What's the size of the directory? If P is the number of processors that you have in the system. If you have tens of terabytes of memory, if you have cache blocks of 64 bytes, you divide 10 terabytes by 64 bytes and multiply by p+1. That's the number of bits you have in the directory. That's actually a lot larger than your caches, actually, in fact. Okay, but assume that you have it somehow. You have 1 bit for each cache, indicating whether the block is in the cache, that local cache or local processor. In this case, processor and cache can be used interchangeably because we're assuming a processor is a private cache. And we also have another bit, exclusive bit, saying that a cache whose bit is set has the only copy of the block and can update it without notifying others. So there could be optimizations that you can do, basically. This directory can grant permission to a cache that requested to update a cache block, saying that, okay, you have the cache block, you can update it until I take away your permission. And you don't need to notify me while you're updating this, because I guarantee that no other cache has this block, right? So basically, you can do a lot of interesting optimizations with directories. So on a read, the directory, the cache sends a message to the directory, and the directory sets the cache's bit in the directory entry for the block and arranges the supply of the block into the cache. If it was updated by some other processor, for example, it takes the data block from that processor and gives it to the processor that's reading it, right? And on the right, the directory makes sure that it invalidates the block in all caches that have the block and resets the bits of those caches in the directory entry for the block, because it's going to give the cache block to someone so that someone can update it, right? And we have an exclusive bit associated with each cache block in local caches so that the cache can know to update the exclusive block silently without notifying the directory. So if it got permission for this cache block from the directory, it sets its bit called the exclusive bit in the tag store, saying that, oh, I'm accessing this block and the exclusive bit is set, which means that I know now that I'm the only cache that has the copy in the system, and I can silently update it without going through the directory. Okay, or I can read it also without going through the directory, right? Okay, make sense? So now you know the two basic coherence methods. It's important to know, I think, this much. If you want to know about optimizations, you'll have to take the future courses. And this is, for example, the state machine for each cache block that's implemented in Pentium Pro processor. It's called the MESI protocol. The protocol that I showed you was valid-invalid. Actually, with the directory, we looked at an exclusive bit. MESI is, there's 4 bits, basically 4 states: invalid state, exclusive state, shared state, and modified state for each cache block, basically. Exclusive means basically I have the only copy of the cache block, so I can write to it. Okay.